Welcome to our deep dive into the fascinating world of D and F block elements. In this video, we'll unravel the mysteries behind these unique groups on the periodic table. Often referred to as transition and intertransition elements, the D and F block elements play crucial roles in chemistry and industry. From their position in the periodic table to their remarkable properties, these elements are truly special. Let's begin by understanding what sets them apart and why they're so important in both nature and technology. Get ready for an exciting journey through the heart of the periodic table. D-block elements, commonly known as transition metals, occupy groups 3 to 12 of the periodic table. These elements are characterized by the filling of their d orbitals, which gives them unique chemical and physical properties. Transition metals like iron, copper, and nickel are essential for various biological and industrial processes. Their ability to form colored compounds, exhibit variable oxidation states, and act as catalysts makes them incredibly versatile. Let's explore what makes these elements stand out and how they contribute to our daily lives. If you look at the periodic table, you'll notice the D-block elements are situated right in the center. These elements bridge the gap between the S and P blocks, making them a central feature of the table. Their unique position allows them to connect different groups of elements, both chemically and physically. This central location is not just a coincidence, it reflects their transitional nature and the important role they play in the periodic trends and properties of element. Electronic configuration of D-block elements is a key factor in their behavior. Typically, these elements have their outermost electrons filling the d orbitals, specifically n1d and ns orbitals. This configuration leads to a variety of oxidation states and complex bonding patterns. For example, iron can exist as Fe2+ or Fe3+, depending on how many electrons are lost. This flexibility is what makes transition metals so useful in chemical reactions and industrial applications. Transition metals are known for their impressive physical properties. They are typically hard, have high melting and boiling points, and are excellent conductors of heat and electricity. These characteristics make them ideal for use in construction, electronics, and transportation. Their metallic luster and malleability also contribute to their widespread use in manufacturing and technology. Let's take a closer look at how these properties benefit our everyday lives. Chemically, D-block elements are incredibly versatile. They can form a wide range of compounds, often displaying vibrant colors due to dd electron transitions. Their ability to adopt multiple oxidation states allows them to participate in various chemical reactions, including redox processes. Many transition metals also act as catalysts, speeding up important industrial reactions like the Haber process for ammonia synthesis. Their reactivity and adaptability are key reasons why they're so valuable in chemistry. One of the most distinctive features of D-block elements is their ability to exhibit variable oxidation states. Unlike S and P block elements, which usually have fixed oxidation numbers, transition metals can lose different numbers of electrons. This property allows them to form a variety of compounds and participate in complex chemical reactions. For example, manganese can exist in oxidation states ranging from +2 to +7, each with unique chemical behavior. Transition metals are famous for forming colored compounds. This is due to the dd electronic transitions that occur when light interacts with their d orbitals. These colors are not just beautiful, they're also useful in analytical chemistry and industrial processes. For instance, the deep blue of copper sulfate and the vivid green of nickel compounds are classic examples. These colors help scientists identify and analyze different elements and their compound. Many D-block elements serve as catalysts in both biological and industrial processes. Their ability to change oxidation states easily allows them to facilitate chemical reactions without being consumed. For example, iron is a key catalyst in the Haber process, while platinum is used in catalytic converters in cars. These catalytic properties are essential for efficient chemical manufacturing and environmental protection. Some D-block elements, such as iron, cobalt, and nickel, are magnetic. This property arises from the presence of unpaired electrons in their d orbitals. Magnetic materials are crucial in technology, from electric motors to data storage devices. The study of magnetism in transition metals has led to significant advancements in electronics and engineering, making our modern world possible. Transition metals are known for their ability to form complex compounds with ligands. These complexes are important in both biological systems and industrial applications. For example, hemoglobin, the oxygen-carrying molecule in blood, is a complex of iron. In industry, complexes of platinum are used in cancer treatment drugs. The versatility of transition metals in forming complexes is a key aspect of their chemistry. D-block elements are essential in the formation of alloys. Alloys like steel, bronze, and brass are made by combining transition metals with other elements. These materials have enhanced properties such as strength, durability, and resistance to corrosion. The ability to form alloys has revolutionized construction, transportation, and manufacturing, making D-block elements indispensable in modern industry. Now let's shift our focus to the F-block elements, also known as intertransition elements. These elements are found in two rows at the bottom of the periodic table, the lanthanides and actinides. The F-block elements are characterized by the filling of their f orbitals, which gives them unique chemical and physical properties. Let's explore what makes these elements so intriguing and important. Lanthanides are the first series of F-block elements, ranging from atomic numbers 57 to 71. These elements are known for their high reactivity, especially with water and air. Lanthanides are used in a variety of applications, including magnets, lasers, and lighting. Their unique electronic configurations give rise to interesting magnetic and optical properties, making them valuable in advanced technology. Actinides make up the second series of F-block elements, with atomic numbers 89 to 103. These elements are mostly radioactive and include well-known elements like uranium and thorium. Actinides are crucial in nuclear energy and medicine. Their ability to undergo fission reactions makes them important for power generation and scientific research. Let's see how actinides are shaping the future of energy and technology. Block elements are characterized by the progressive filling of the 4f and 5f orbitals. This unique electronic structure leads to a wide range of oxidation states and complex chemical behavior. For example, cerium can exist in both +3 and +4 oxidation states, while uranium can have even more. The f orbitals are deeply buried, which affects the chemical reactivity and bonding of these elements. Block elements display a variety of physical properties. Lanthanides are typically silvery white metals, soft, and have high melting points. Actinides, on the other hand, are mostly radioactive and can be quite dense. These properties make F-block elements useful in specialized applications, from high-strength magnets to nuclear reactors. Their unique characteristics set them apart from other elements on the periodic table. Chemically, F-block elements are highly reactive, especially the lanthanides. They readily form compounds with oxygen and halogens. Actinides are even more reactive, with many being radioactive and capable of forming a wide range of compounds. Their reactivity and radioactivity make them both valuable and challenging to handle, requiring special precautions in laboratories and industry. Unique phenomenon among the lanthanides is the Lanthanide contraction. As you move across the series, the atomic and ionic sizes decrease gradually. This occurs due to poor shielding by the F electrons, leading to a stronger attraction between the nucleus and the outer electrons. Lanthanide contraction affects the chemistry of subsequent elements and has important implications for the periodic table. Lanthanides are used in a wide range of modern technologies. They are essential in the production of strong permanent magnets, which are found in headphones, speakers, and electric vehicles. Lanthanides are also used in lasers, phosphors for color television screens, and as catalysts in petroleum refining. Their unique properties make them indispensable in high-tech industries. Actinides, especially uranium and plutonium, are vital for nuclear power generation. These elements undergo fission reactions, releasing enormous amounts of energy. Actinides are also used in medical imaging, cancer treatment, and scientific research. Their radioactive properties require careful handling, but their contributions to energy and medicine are invaluable. Most actinides are radioactive, meaning they emit radiation as they decay into more stable forms. This property is harnessed in nuclear reactors and medical treatments, but it also poses safety risks. Proper containment and handling are essential when working with radioactive F-block elements. Understanding radioactivity is key to safely utilizing these powerful elements. While both D and F-block elements are transition elements, they have distinct differences. D-block elements are generally less reactive, have higher melting points, and are more commonly used in everyday materials. F-block elements, on the other hand, are more reactive, often radioactive, and find use in specialized high-tech and energy applications. Understanding these differences helps us appreciate the diversity of the periodic table. Transition metals are all around us. From the steel in our buildings to the copper in our electrical wires, these elements are essential to modern life. They're also found in coins, jewelry, and even in our bodies as trace elements. Their strength, conductivity, and versatility make them the backbone of countless industries and technologies. Transition metals, especially lanthanides, are crucial in advanced technology. They're used in smartphones, computers, and renewable energy devices. Rare earth magnets made from lanthanides are key components in wind turbines and electric vehicles. The demand for these elements is growing as technology advances, highlighting their importance in our future. Extraction and use of D and F block elements can have significant environmental impacts. Mining these elements often leads to habitat destruction, pollution, and waste. However, advances in recycling and sustainable mining practices are helping to reduce these effects. Responsible management of these resources is essential for a sustainable future. D-block elements like iron and zinc are vital for life. Iron is a key component of hemoglobin, allowing our blood to carry oxygen. Zinc plays a crucial role in enzyme function and immune response. While most F-block elements are not found in biological systems, their compounds are used in medicine and imaging. The intersection of chemistry and biology highlights the importance of these elements. Extracting D-block elements from ores involves complex chemical processes. Methods like smelting, electrolysis, and reduction are commonly used. These processes require significant energy and resources, but they yield metals that are essential for industry. Advances in extraction technology are making these processes more efficient and environmentally friendly. Extraction of F-block elements, especially lanthanides, is challenging due to their similar chemical properties. Techniques like solvent extraction and ion exchange are used to separate them. Actinides, being radioactive, require special handling and containment. The complexity of extraction adds to the value and rarity of these elements. Recycling transition metals is becoming increasingly important as demand rises. Metals like copper, nickel, and iron can be recovered from scrap and reused, reducing the need for mining. Recycling not only conserves resources but also minimizes environmental impact. Innovations in recycling technology are making it easier to recover valuable metals from electronic waste and other sources. Recycling F-block elements, especially rare earths, is more difficult due to their chemical similarity and low concentrations in waste. Specialized processes are required to separate and purify these elements. Despite the challenges, recycling is essential to ensure a sustainable supply for high-tech industries. Research is ongoing to develop more efficient and cost-effective recycling methods. Future of D block elements looks promising, with ongoing research into new alloys, catalysts, and electronic materials. As technology advances, the demand for transition metals will continue to grow. Innovations in extraction, recycling, and material science are ensuring that these elements remain at the forefront of scientific and industrial progress. F block elements are set to play an even greater role in the future, especially in energy and technology. Advances in nuclear power, medical imaging, and renewable energy rely on the unique properties of lanthanides and actinides. Continued research and sustainable management will be key to unlocking their full potential. D and F block elements illustrate important trends in the periodic table, such as changes in atomic size, ionization energy, and reactivity. Understanding these trends helps chemists predict the behavior of elements and design new materials. The periodic table is more than just a chart, it's a powerful tool for scientific discovery. Both D and F block elements are central to coordination chemistry, where metal ions bind to molecules called ligands. This field has led to the development of new drugs, catalysts, and materials. Coordination compounds are used in medicine, industry, and research, showcasing the versatility of transition and inter-transition metals. Unique electronic structures of D and F block elements give rise to interesting spectroscopic properties. These elements absorb and emit light at specific wavelengths, which is useful in analytical chemistry and material science. Spectroscopy helps scientists identify elements, study their behavior, and develop new technologies. Many F block elements, especially the lanthanides, exhibit strong magnetic properties. These elements are used to make powerful magnets for electronics, motors, and medical devices. The study of magnetism in F block elements is advancing our understanding of materials and enabling new technological innovations. Actinides, particularly uranium and plutonium, are at the heart of nuclear technology. They power reactors, submarines, and even spacecraft. The ability of these elements to undergo fission reactions makes them invaluable for generating energy and exploring new frontiers. Nuclear applications highlight the power and potential of F block elements. Both D and F block elements have important medical applications. Platinum compounds are used in cancer treatment, while gadolinium, a lanthanide, is used in MRI contrast agents. These elements help diagnose and treat diseases, improving healthcare outcomes. The intersection of chemistry and medicine continues to yield life-saving innovations. The vibrant colors of transition metal compounds are not just for the lab, they're found in paints, ceramics, and glass. Cobalt blue, chromium green, and manganese violet are just a few examples. These colors are prized in art and industry, showing how chemistry adds beauty to our world. Many F block elements, especially lanthanides, exhibit luminescence. They emit light when excited. This property is used in lighting, lasers, and display technologies. Europium and terbium, for example, are key components in fluorescent lamps and television screens. Luminescence showcases the fascinating behavior of inter-transition elements. Supply of D and F block elements is subject to geopolitical and economic challenges. Many of these elements are concentrated in a few countries, making supply chains vulnerable. Efforts are underway to diversify sources, improve recycling, and develop alternatives to ensure a stable supply for industry and technology. Ongoing research into D and F block elements is leading to new discoveries and applications. Scientists are exploring new materials, energy solutions, and medical treatments based on these elements. Innovation in chemistry is driving progress in technology, healthcare, and sustainability. Sum up: D and F block elements are at the core of modern science and technology. Their unique properties, from variable oxidation states to magnetism and luminescence, make them essential in countless applications. Understanding these elements helps us appreciate the complexity and beauty of the periodic table, and their continued study promises exciting discoveries ahead. As we look to the future, the study and application of D and F block elements will only become more important. From powering our cities to advancing medicine and technology, these elements are shaping the world of tomorrow. By understanding their properties and potential, we can harness their power for a brighter, more sustainable future.